Hello and welcome back. In this module, we will be covering the endlessly fascinating topic of subsetting. This includes subsetting atomic vectors, matrices, arrays, lists, and data frames. And we will be following roughly chapter 4 of Advanced R 2nd edition. So please take a look at that as well for an additional perspective. Okay, so I have the file open, subsetting.r, and I'm in Emacs here. I'm going to start an R session. And let's get started. So I'm just going to demonstrate some of these things, create a vector A. Let's look at what A is. You can probably guess. It's the numbers 1, 4, 9, 16. Each element is the square of its index. And subsetting, there's various ways to do it. For atomic vectors, the way to do it is with square brackets. So if I do A square bracket 3, it's going to pull out the third element of A. So this is going to be 9. You can also give it a vector of indices. So if I give it the vector 3, 4, let me just run this. So that's the vector 3, 4. If I say A square bracket 3, 4, I get the third and the fourth entry. By the way, sometimes I'll say things like A of 3 and 4 or the 3, 4 indices of A. These things don't necessarily need to be in order. So I could say A4, 3, and it will give me A4 and then A3 in a vector. So 16, 9. And I can repeat values. This ends up coming in handy quite commonly. So if I say A1, 1, 2, 2, 3, it's going to return the first element of A twice, the second element of A twice, and then the third element of A. So that should give 1, 1, 4, 4, 9. R also allows you to give negative indices. What a negative index gives you is it's going to return A, but it's going to omit the indices that have negative values. So if I say A minus 1 minus 2, it's going to return A with the first and the second index removed. So this should give 916. However, you can't mix negative with positive indices. So here, what we're telling R to do is to remove the first entry and then take the second entry. And it's not clear what you mean by that. So R gives an error for that. If you try to give it an index that's not in the range, remember A has length 4. If you ask for the 6th index, it just gives an NA. By the way, it doesn't change A. A is the same. If I give a missing index, if I say 3NA, let me just remind you what this is, 3NA. And as for that, it will return an NA for the NA index. Okay. We saw in the last video that you can have atomic vectors with a names attribute. And one way to create them is in the assignment in the C function, is to give each element a name. So this is going to be a vector of length 3. The first element is named E, and its value is E to the 1, or E, 2.72 something something. Second element is named pi, and its value is pi. Note that these two instances of pi mean two different things. So on the right side of the equal, it means the value pi. And on the left side of this equal sign, it's a name for this particular value. And then we also have tau, which is equal to 2 times pi. So if we run this, let's look at B. So that's B. It prints out the values and the names above them. And if we pull out the first element, it's going to keep the name attribute. We can also use the names to do subsetting. So this is like a this operates kind of like a dictionary in Python. So I could say B of character E, and that gives the value. I can give multiple names, and it will return them. But I can't mix characters with index. So if you think about what's going on, this makes perfect sense. So basically the order of operations here is it evaluates this vector. So before I run this, think about what this is going to return. I'll give you a second. If I run this, this is going to coerce the 3 to a character 3. And if I try to access an element of B named character 3, it's going to tell me that no such element exists, and it returns an NA. We can also subset vectors with logical vectors. So up here, we're telling it which index we want. We can also give it a vector of trues and false, and that will also act to subset. So let's see how that works. So I can do this logical comparison B greater than 4. What this line does is it looks at each element of B, compares it to the number 4, and tells us whether that element is bigger than 4. So if we look here, E is 2.72, so that's less than 4, you get a false. Pi is 3.14, less than 4, you get a false. Tau is 6.28, it's bigger than 4, so you get a true. By the way, this is equivalent to saying B greater than 444. False, false, true. What ends up happening here is it does recycling. So it recycles the vector 4 here, or the number 4 here. Okay, so B greater than 4 gives this logical vector, false, false, true. And if I try to subset B using that logical vector, what it's going to return are the entries of B for which the logical vector is true. So if you look here, the first one was false, the second was false, and the third is true. And so it's only going to return the third element of B. So that's when you give it a logical vector that's the same length as the vector B. Let's see what happens. If I give it just a vector true, I think what's going on here is this true gets recycled 3 times, and so you just get all 3 values back. If I do true false, it gives me E and tau. So if you can imagine what happens with the recycling, it's going to do true false, and then it's going to start over with true to fill out the third element. And so that's why you get E and tau. There's a function it's useful called which. So what which returns is if I give it a logical vector, it tells me which of these entries of the logical vector are true. So if I run this, it should say 1, 3. Because the first and the third are true. If I do which B greater than 4, this should give me 3, because only the third element was greater than 4. And therefore, you can combine these logical comparisons, B greater than 4, with which in order to do subsetting. But of course, there's no, well, we'll see there's a slight difference here, but in many cases, there's no reason to apply which, because you can just do directly B of B greater than 4. Okay. Now there is one difference that could be of some consequence sometimes. So if I take B and I append an NA, so what we're going to do is look at what happens when we have missing values in B. And I do B greater than 4, it's going to say false, false, true, NA. So it's the same for the first 3, but when it gets to the NA, it says I don't know what to do with that, so I'm just going to return an NA. And if I try to input this false, false, true NA vector to subset B, it gives me the tau, but it also gives me an NA. So this may or may not be what you're trying to do. So say you're trying to subset a big long vector according to some criterion, and that vector has missing values, and you don't care about the missing values, you just want to ignore them, then you'll want to use which in conjunction with the logical vector. So remember, if I do which b greater than 4, which will just drop the missing values. And so if I do b of which greater than 4, it just gives me the third element. Okay, so that's atomic vectors, and you'll be using this stuff over and over. You know, it's kind of interesting. This subsetting is a pretty dry topic, I'll have to admit. But it's something that you use so often when you're coding in R that in advanced R, he dedicates a whole chapter to it. And in this class, we're dedicating a whole week to studying it. And I think that's justified given how much you use subsetting as an R programmer. All right, so let's move on to matrices. And we're just going to create a matrix. Here I'm using the outer function. If you're not familiar, you can look at the documentation. This ends up being a really handy function. So basically I give it, in its first two arguments, two vectors. So 1 to 4 and then 1 to 3 multiplied by 0.01. So it's a length 4 vector and a length 3 vector. And I tell it what operation I want to apply to every pair of these two elements. And what it's going to return is a matrix with that operation applied to every element. So if we look at M, what happens is, so the first element is 1 plus 0.01, so the 1, 1 element. Here it applies plus to 1 and 0.02, and here it applies plus to 1 and 0.03. And you can give it other operations here. So for example, let's just look at this. If I do multiply, I get that. You can do divide. I think you can even do things like paste. So to treat them as characters and put them together. Okay, so let's stick with plus though. So if I want to pull out this entry, this is the 1, 2 entry of M, I can do it with this double indexing. So M square bracket 1 comma 2, this will pull out the 1, 2 entry. I can also give vectors to these two, you think of them as arguments to M. So if I do this, I'm going to pull out the first 2 rows of the second column. And notice what happens here is, even though we can think of this as a submatrix of M, R does an automatic coercion to a atomic vector. So if I do, let's see, dim M, M has a dim attribute, and therefore it's a matrix. But if I do dim M1, 2, comma 2, because it coerces to a vector, the dim attribute is now null. So the result of this subsetting is to return an atomic vector. Same for this, first 3 entries. And then if I want all of the entries from the second column, I can just leave it blank. So this is equivalent, if you've done MATLAB, to doing this colon operator. But in R, you just leave it blank. And likewise, I can pull out the 4th row by leaving the column index blank. Okay. Now, like I said, when you pull out a submatrix that can be coerced to a vector, R will do it automatically. Let me just show you what it does when you're not pulling out a submatrix. So let's do this. So I'm pulling out the first 3 rows and columns 2 and 3. Here it returns a matrix. But if you're just pulling out a column, it coerces. Now if you want to suppress that behavior, there's a way in R to do that. And essentially you you could think of this as an argument to your matrix subsetting, and you say drop equals false. So if I do this, then you can see that R is still treating this as a matrix, and I can confirm that M2 drop equals false. It has a dim attribute. And the same thing works for rows. Okay. Now, a matrix is kind of inherently a two-dimensional object, but remember that in R, a matrix is simply a vector that has a dim attribute. And therefore, we can pull out entries of the matrix by treating it as a vector. So what this will do, M5, this will pull out the fifth element of M. And I'll stop for a second for you to think about which element that's going to be. And let me print out M for you. If I run this, I get 1.02. So why is it 1.02? Remember that for matrices, R does column major ordering. So the fifth element is going to be 1, 2, 3, 4, 5, 1.02. You can also give it multiple elements. So 1, 6, 11 should pull out this one, and this one. So let's run that. That's right. And I can also tell it to omit entries. So if I want to return everything but the second element, 2.01, I do this. You can also use this to do logical comparison. So if I do M greater than 4, it returns a matrix. Actually, let me put this here so we have it. M greater than 4 returns a matrix. And if I do subsetting with that, it will return this vector. Okay. And note that whenever you do vector style subsetting, R is coercing the output to a vector. Okay. All right, let's take a look at this. So there is a third way to subset a matrix. Let's see. If I do this, all right, we did this before, so this pulls out the same thing. This is the which version of this operation, so it returns the same things. With the which function, let's see, which M greater than 4, this returns indices where you're treating R like treating M like a vector. This is the fourth one, 8th one, 12th one. However, you can tell R that you want to return values that treat M like a matrix. So if I add this argument r.end equals true for array.end equals true, and I apply the which function, what this is telling me is which elements of M, in terms of their row and column indices, are greater than 4. So row 4, column 1, that's that one. Row 4, column 2, that's that one. And row 4, column 3, that's that one. And you can actually use this to do subsetting. So what's happening here is I'm giving this a single, think of this as an argument inside of square brackets. And what this is a matrix with 3 rows and 2 columns. And what's going to get returned are the elements of M in the row column indices given by this object. So this does the same thing. Okay. All right, so let's see what happens here in some other cases. So this is kind of tricky because of how this interacts with automatic coercion. So for example, what if I don't want all 3 of these elements, I just want this element? So one way you might think about doing that is to say, well, I'm going to apply this which function, and then I'm going to pull out the second row of that. That's 4, 2. But if I apply M here, you can guess what happens. It's going to pull out because this is coerced to a vector, it's going to pull out the fourth element and the second element. Let's see. Fourth element is, let me print out M again so we can see that. Fourth element is 4.01, and the second element is 2.01, which is probably not, if you wrote this code, that's probably not what you wanted it to do. Okay, so what's going on is that this is an atomic vector, this object. And the way to make it do what you want to do is to make sure when you pull out the second row of this which object, you use drop equals false. So this treats it as a matrix, a 1 by 2 matrix, and you apply that and you get the thing that you wanted. Now arrays are just, you can think of that as a multi-dimensional matrix. And subsetting for arrays works very similar to how it works for matrices, except there's going to be an extra index. So let's create an array. I'm going to use the array function, and I'm going to, inside the elements of the array are going to be the letters from 1 through 12. Let me show you what these are. Letters is an object that's just in R. And the dimensions of this array are 2, 3, 2. So 2 rows, 3 columns, 2 slices. And I'm choosing this because 2 times 3 times 2 is 12. So everything's going to work out nice. Print that out. That's what it looks like. And remember, it does row, column, slice, major ordering. So A, B, C, D, E, F, G, H, I, J, K, L. So to pull out the element of ARR in the second row, first column, second slice, let's see what that is. So I like to do this backwards. So second slice, first column, second element, or second row, should be an H. So let's run that. We get H. And so this is similar to this double indexing for matrices, except of course this array is a 3-dimensional object, so you need to give it 3 things. You can also treat an array as a vector. An array is simply a vector that has a dim attribute, just like a matrix. And so you can pull out the 5th element. So if you can guess what this is going to be, it should be 1, 2, 3, 4, 5. So it should be E. And you get E. Okay. Now, one thing to be careful about is this works just like matrices, but with arrays, it can kind of be, you're kind of like, it feels like you want to give it a vector of things. One reason is that when you define an array, the argument, this dim argument, is a vector as opposed to a matrix. Let's see, matrix, yeah. A matrix, the number of rows and the number of columns are separated into 2 separate arguments. So you might think that arrays will work similarly. If you do C212, you're going to just get the 212 element, but no, this will give you BAB. So it takes the second element, then the first element, then the second element. Okay. So if you want to do indexing like this, you can do the same thing that you do for matrices. So you can create a matrix of those indices and then give it that. And this is just a 1 by 3 matrix, but of course you could have an n by 3 matrix of indices and it will return the values. So 2, 1, 2 is of course H. All right, so that's how you use subset, vectors, matrices, arrays. You can also use subsetting to do assignments. So we saw something kind of similar to this when we talked about replacement functions. So it turns out that vectors, matrices, arrays can use a similar syntax to assign specific values to specific elements of these objects. So let's create a couple of objects here. We're just going to look at atomic vectors. So A is the same vector we had before, and then B is this other vector we had before. So if I want to just change the 4th element of B, I put b square bracket 4 on the left side of the assignment operator. And then I put whatever value I want to assign to that element to the right side. So the way you read this is we're assigning the first element of A to the fourth element of B. So if we run this and we look at the value, it took this NA and it assigned that element the value 1, which was the first element of A. Okay, so that works, and it works kind of how you think it should work based on looking at the code. You can also combine replacement functions with assignments. This looks a little bit weird, but this is perfectly allowed. So what this is saying is I'm going to look at the fourth element of the names of B, and I'm going to assign it the value character string 1. So if I do this and this, now before I didn't have a name for that, I didn't have a name for this element. Now the name is the character 1. Okay. You can also do assign multiple values at once. So if I want to assign the second element of A to the first 3 elements of B, I can do that. So that's 4, 4, 4, 1. And I can also do, let's see, what does happen here? B of 4. So this will work, but it gives me a warning. So I'm looking at, this is a length 2 vector, and I'm trying to put it into a place where I only have room for one value. And it's saying number of items to replace is not a multiple replacement length. So R doesn't give you an error here. It lets you do it, but it gives you a warning because this is probably not what you intended to do. And what it did is it just took, so it looked at A, let's just print this out, A, C, 4, 3. It tried to put this into a container that only contains one element. And what it did, it just took the first element and put it in there, so the 16. Okay, so again, this is probably not what you want to do, and so R gives you a warning here. However, so the warning here is number of items to replace is not a multiple of replacement length. So you might get unlucky and say, this is also probably not something you will commonly intend to do, to take this length 2 vector and put it in a container that holds 4 things. But there's no warning here. So what this does is it recycles the values 1, 4 twice and puts them in B. Okay. One more thing is you can also do this. This just returns all of B. This isn't used that commonly, but one maybe nice use case of this is you can use this to take a single value and fill in the entire vector. So this retains B as a length 4 vector, but puts 0 in every element. Of course, this is different than doing this. If I do this, then I'm reassigning the object B to a length 1 vector 0. So these are two different things. So this can be useful sometimes. Okay, so let's see how this works with matrices. It works just how you think it will. So let's create our matrix M again. So that's M. If I want to put 999 in the 4, 3 element of M, I just do this. So the M 4, 3 is on the left side of the assignment, 999 is on the right. And I print that out, and now I have 999 down here. That's pretty straightforward. You can also treat M as a vector and do assignment this way. So if I run this, it should take the 9th element, which is this one, in column major ordering, and assign it the value 888. Run that, look at M. Okay, that did what I think. And then you can also use this matrix style indexing as well. So let me just show you what this is. This is a 1x2 matrix. And so what this is going to do is it's going to assign the value -1 to the 3-3 entry of M, which is this one right here. Okay. And then everything works the same for arrays as well. So let's look at our array. I'm going to take the 1, 2, 1 element of ARR and assign CCC. So I turn the C into a CCC. I'm going to turn the 5th element, which is this one, by column major ordering. And now it's EEE. Okay, so assignment is pretty straightforward. It sort of does what you think it does. Also, with matrices and arrays, you can use this this type of operation. So I can say oh, this should be ARR. So it retained the shape of ARR, but filled in the value gone to every element. All right, so now let's move over to lists. Lists are a bit more complicated, mostly because a list is simply it's a more complicated object. So let's create a list to work on. So if we look at this list, it has 3 elements. The first list element is an atomic vector with the values 1, 2, 3, 4. The second list element is a matrix, 4 by 3 matrix with NAs in every entry. And the third list element is a function. Now, we haven't talked about functions as objects yet, but we will. But suffice it to say that a function is an object, and so you can put it in a list element. Okay. So there's at least 3 ways to subset lists, and they can do different things. So this is important. You can subset a list with single square brackets, just like you do with atomic vectors. But what gets returned is a list. So if I say A of 1, what I'm asking for is a list containing the first list element. So you can see that it is a list because it has this double bracket thing here. And I can check, what does it say? Is.list A1. And that's true. I can also say class A1. So that's a list. That pulls out the list containing the second list element. Note that since this is a list, A square bracket 2 is a length 1 list, this becomes a 1, whereas if I just look at A, that is a 2. So what this returns is a list of length 1, even though you're pulling out the second element. And same thing for A3. Now you can give it multiple elements. So what gets returned here is a length 2 list containing the first list element of A and the second list element of A. Okay, so this kind of does what you think it does, but remember when you use square brackets to subset a list, you get a list back. So it always returns a list. Now if you want to pull out the element of the list, you have to use double square brackets. So what this syntax does is it pulls out the object that's in the first entry of the list. So this is going to be a vector. So if I do class A1, this is no longer a list. This is telling me that it's an atomic vector filled with integers. That's the second element. It's a matrix, not a list containing a matrix. And this is the function. Now you can combine this double square bracket with other operators. So what this does is it pulls out the second list element, which is a matrix, and then I can apply any sort of matrix syntax to that. So this will pull out the 4-3 element of that object, which of course is NA because they're all NA. But I can also do things like assignment. So that will assign 0 to the 4-3 element of the second list element of A. So if I print that out, I see now there's a 0. And I can also grab that element here and confirm that it's 0. This also works for functions. So remember, the third list element is a function, and I can call that function by appending the syntax for calling functions, which is the round brackets. So this will square the number 7, and you'll get 49. Okay. All right, so things can get pretty complicated here by combining these different operations. So let's think about what this one is going to do. So this part should pull out these a list containing the second list element, and then this should pull out the value inside, which is a matrix, and get the 4-3 entry. So this should give 0. Again, we can't put a 2 here, so even though this is the second, we're pulling out the second list element, what gets returned by this is a list of length 1. So this should give some kind of error. Yeah, this is an error. And so this is a 1. A list is also sometimes referred to in R as a hierarchical data structure. And so you can give it things like this. So this syntax with square brackets is the same as saying A double square bracket 1, then double square bracket 2. So what happens here? So this gives the element 2. So I'm looking at the object in the first list element, and I'm grabbing the second value. Now this is a little strange because this is an atomic vector, and we haven't yet talked about a double square bracket index subsetting of atomic vectors. So why did that work? Well, the answer is simple, is that you can subset atomic vectors with double square brackets. So if you do this works just as well. And in the advanced R book, he actually makes a recommendation that you should consider using double square brackets for indexing or subsetting atomic vectors, and I'm not sure I'm there yet. I'd have to be convinced more that that's a good idea. It's for one, it's more to type. All I mean is these do the same thing. All right, there is yet another way to, well, there's actually a couple more ways to subset lists. So if the list has names, so I'm assigning the names vec, mat, fun to A, I can access the elements of that list with the $sign operator. So what this is going to do is I'm going to extract the list element whose name is vec. And if you'll notice here, what gets returned is not a list, it's the object inside that list element. So this operates similarly to the double square bracket operator. This pulls out the matrix, this pulls out the function, and you can also combine operators here. So this will apply the function to the number 12, so this should give 144. And this works for matrices and vectors as well. So mat 4-3 should give 0. Okay. Now if you have a named list, you can also access its elements using the names, but with the square brackets. So what this does is it pulls out a list containing the first list element. So again, single square brackets returns a list, and then you can do the same thing with double square brackets. This returns the object. And let's just confirm that. Class A vec, that's a list, whereas class A vec is atomic integer vector. One thing to be wary of is that this $ thing, for convenience, they allow it to do partial matching. So if we do this, this actually works because there's no other element that this could match to, and we're definitely looking for MAT. However, this does not work. This is a bit weird to me, and probably if you did this, most likely you've made a mistake, and you want to try to keep your code free of mistakes. And so just for safety, I really, in my code, I try to use double square brackets in this format rather than the $. It's obviously easier to type a $MAT than a square bracket, quote, MAT, quote, square bracket. But this is a little bit safer for code that you want to really work without silent bugs. Okay, so null has an important role in eliminating list elements. So let's create our list again. So A has these 3 objects in it. If I assign null to one of the list elements, what it does is it gets rid of that element. So now it's just a list with 2 elements. It's gotten rid of that fun element, which was the 3rd one. This works in other types of subsetting. So it works this way too, same thing, and it works this way too. Now this is different from how vectors work. So let's say B is 1 to 10. And I want to say, I want to get rid of the 10th element. If I run this, I get an error. So what's happening here is it's saying, here it's treating null as a generic length 0 object, and it's trying to put it in this length 1 container, and it's getting an error. But for lists, it interprets this as, I just want to get rid of whatever is in that list element. So null operates a little bit differently for lists than it does for vectors. Okay. Now we talked about data frames last time, and data frames share properties of matrices and lists. So let's see how subsetting works for data frames. So I just made a silly little data frame with the letters A through J and the numbers 1 through 10 and column names lets and nums. If I want to pull out one element, I can treat it as a matrix. So this should pull out E. It's the element in the 5th row, 1st column, which is that one. If you pull out a single column, R will automatically coerce it to an atomic vector. Remember that a data frame is a list whose list elements are all vectors of the same length. So if I do this, it will pull out the 1st column, and in addition, it will coerce it to a vector. So this is no longer a data frame. That's the 2nd one. However, if you pull out a row, R will not do the coercion. So that pulls out the 5th row, and the class is still a data frame. Reason for that is, well, I don't know if there's a great reason, but the reason that you can coerce a column to an atomic vector is because a data frame is a list whose columns are atomic vectors. However, the rows may have different types along the different columns, and so R doesn't automatically coerce this to anything. Okay. You can pull out multiple columns at the same time. So this will pull out columns 2, then 1. That just reverses the order of the columns. And you can also repeat the columns. And you notice what R does here is, since the column names have to be unique, it assigns a column name to this 3rd column, which is the same as the 1st one, but it appends .1 so that it's unique. Single indexing also works for data frames. If you use this single square bracket with a single argument, meaning one number, not two numbers separated by commas, it's going to treat dat as a list. So this will pull out the first list element, which is the first column, which are the letters. And notice that it does not coerce it to a vector. So if you want to pull out columns, but retain the data frame object class, then you should do it with square brackets. This pulls out the second one. Again, this is a data frame, not an atomic vector. And then you can also pull out multiple columns with single square brackets. Okay. And like I said before, if you give it multiple indices with square brackets, it will treat it like a matrix. Okay. You can also combine this single square bracket subsetting with names. So you can pull out the column names. This operates similarly to how named matrices work. So if that were a matrix and one of the columns was named lets, it would pull out that column. So that's what it does for data frames as well. However, here it will coerce it to an atomic vector. Here it keeps it as a data frame, and here it also keeps it as a data frame. If you just give it a name, so here we're treating it like a list. We're trying to pull out the list element named lets. This will keep it as a data frame. This also keeps it as a data. These all keep it as a data frame. List, remember we saw above, you can access list elements with $. You can do that with data frames as well, but this coerces to a vector. And you can combine subsetting of the data frame with the normal operations you can use on atomic vectors. You can also do a double square bracket. So if we do this, this coerces to an atomic vector. And this makes a lot of sense. So if we're thinking of dat as a list whose elements are vectors of the same length, what I'm doing here is I'm pulling out the object that's in the first list element, which is the atomic vector letters A through J. So this makes perfect sense that dat double square bracket 1 gives that, but dat single square bracket gives a data frame. Of course, you can combine things as well. You can also do this. This is a little weird. So this uses kind of the hierarchical structure of lists. So it's going to pull out the first list element and then the third element of that list element, which is a C. And then, of course, you can use the names, and this pulls out the sixth element. So there are many ways to subset data frames. Some of them treat the data frame as if it were a matrix. Some of them treat the data frame as if it were a list. And some of them return atomic vectors. Some of them return data frames. So it's really important to know that really the output of the subsetting operation, or what gets returned, could be a vector, it could be a data frame. So it's really important to know what you're doing there, so you know what your object types are. Okay. Now there's also a subset function. I don't use this all that often, but you should probably know this exists. So what the subset function does, all right, let's look at the documentation, is it returns subsets of vectors, matrices, or data frames. We're going to look at applying this to a data frame, but you can also use it on vectors and matrices, which meet conditions. So let's look at the part for data frames. So X is going to be an object to be subsetted. In this case, it's a data frame. Subset is a logical expression indicating elements or rows to keep. And then select tells us which columns to keep in the case that X is a data frame. Okay, so let's see this in action. So we're going to subset this data frame, dat. The subset we're going to choose is nums greater than 6. So if we apply this, it should give us the last 4 rows of the data frame, and it does. Note that this object, there is no object called nums in the workspace. It's only dat $nums. But when you're using this inside of the subset function, it knows that you're talking about the nums variable inside of the data frame dat. You can also use select to pull out certain columns. So these are things that you do often when you're analyzing data, and you can do it with the subset function. Now this is the same as these operations. So what this does is it treats dat sort of like a matrix. I'm going to pull out the rows for which this vector is true, which is the last 4. So we get the same thing. And here I want to pull out in addition, just the column named lets, and I'm going to apply drop equals false to keep it as a data frame. So these 2 lines do the same as this. In the documentation for subset, they say probably you should just do it this way with square brackets. But I think some people use this, so you should know it exists. And it's a little bit, I don't know if it's less code, but it's a bit more descriptive for what it's doing. I'm taking a subset, this data frame, and this is the subset I'm taking. Okay, so that's it for subsetting. Again, this is probably a low point in the course in terms of dryness of the material, but this is something that you'll be using every day. Learning to subset is like learning to walk. So it's important to know the various ways to do it. And honestly, it can be a bit complicated when you're working with data frames. Okay, that's it.